Life doesn't come with blueprints. It folds, cracks, burns, and blooms all at once. All of us, we stumble through our imagination, carrying ghosts in our silence, trying to stitch meaning from the chaos that we survive. And between that ache and the awe, we find ourselves speaking, not merely to be heard by anybody else, but rather to know who we truly are. I'm Bhavithir V. Bharadwaj. Welcome to episode 43 of Genesis of Tomorrow. The following is a conversation about artificial intelligence, virtual reality, neuro-symbolic models, the essence of truly intelligent systems, and much more with Dr. Andy Banburski-Fahey, a former researcher at MIT in the theory of deep learning and currently an AI researcher at Microsoft. Also, folks, if you're interested in such deep science and deep tech conversations and are able to derive even the slightest bit of value from the show, please support us by clicking the subscribe button so that we can keep improving the quality of the episodes and keep on bringing such wonderful guests over for you. Now, without any further ado, let's get right into it. Enjoy and thank you. And we're rolling now. First of all, formally welcome to the show. Before anything else, a very pertaining topic to your entire area of work, which I found personally very intriguing: neuro-symbolic models. Now, I did some research of my own, and symbolic logic that's got to do with it was generally good with reasoning, planning, in general stuff, rule based stuff. That was for a long time the major approach that researchers and scientists took in regard to development of artificial intelligence. That changed with the advent of deep learning and neural networks, because they were certainly more better at pattern recognition and optimization and all those different other facets that the the symbolic logic lagged. My question to you is to provide a sort of fundamental basis in terms of where do you think this pendulum will settle? Is it entirely this field of research? Is it leading towards a hybrid intelligence of some sort, something better, or is it something that we cannot even imagine as of now?
This is a great question. If you ask it, it's such a broad question that I think I will have to provide some background here, and then maybe we'll see where that goes. But you know, I will say that this field of neurosymbolic research has been around for a while, and in fact, probably for quite a long while before deep learning became really popular. But it really took off more recently. Uh, but the kind of symbolic approach to AI was the original one, or the more popular one for a long time, especially after neural networks completely failed back in the early 90s. But I'll say this: we don't really have a solid neurosymbolic system in existence, so it's really all kind of theoretical conversations. We have some kind of experiments here and there and small networks that are capable of doing things like this. Um, but it is clear, if you're trying to build a system that is capable of doing reasoning and doing, let's say, just math, um, it's clear that systems like R1 and the O reasoning models and things like this are starting to do something interesting, but they're very much not neuro-symbolic systems, because there is no explicit sort of even representation for doing symbolic manipulations. So anyone who does math, we realize that the way that we do math is often very different than just even the kind of things that these models are doing. But you could probably fake a version of this if you build yourself, some kind of agentic system and powered it with some kind of underlying, ability to assign symbols to things. So there are experiments like this, but no model in existence that I'm aware of that really does truly neurosymbolic computations on the scale that is of relevance. So there is a ton of small experiments on language models that have some sort of different architecture that would allow them to do operations just purely on the levels of symbols. Um, Now, I strongly believe that this is where we need to go to truly get to something that would be capable of doing really solid reasoning. The current reasoning models that have become popular are doing something interesting in the sense that they kind of look at their own outputs and then try to build on top of it. It's not fully like recursive reasoning, but it is some sort of slow type of reasoning, and the kind of realm of system one, system two, or slow versus fast thinking. Um, but there's still not very much like assigning, mathematical operations and doing things at the level that math is really done. Uh, and in a way, that partially might be because they have never been exposed to the way that math really happens. Um, and I'll give you an example. If if you were to like just bombard an undergrad in math with just math papers, uh, I don't think they would actually learn from them really well. Even if they had some background and things like in grade school math and things like this, and they knew how to do the kind of they had some algorithms in their head already for doing some basic things. The reality of doing math is that it's really kind of dirty, and you do a lot of you make a small assumption and then you kind of test it. You fill in some you leave some blanks, and these blanks are these symbols that you'll do some operations on, and it is a very complicated process and really dirty in a way. And we know, and then the output at the end of the day that everyone sees is this very polished paper that has like a ton of nice equations, and the reasoning is very clear, but it is not how it really happened in the first place. Uh, and I think because of that, we're throwing these papers, these final outputs at all of these models, so they try to reason in the kind of style that exists in these papers. And most scientific articles are not pedagogically written. They don't explain the reasoning that happened. They explain the very fancy, kind of uh, you know, uh, cleaned up version of it that is not reality of how reasoning happens. Um, so I have a strong belief that for us to actually get to something that would truly be capable of, scientific creativity, of mathematical creativity, we need a system that will be able to do this kind of operations at a very granular level, and that will require some sort of different architecture that allows it to operate, assign some kind of symbolic representation to some kind of object, define structures, and what these symbols exactly mean, and operations that these symbols can take part in, and things like that. So you would need some kind of framework in which you can basically abstract away symbols and operations on symbols, and assign uh, whatever these operations and these rules that these symbols operate on by the language model itself. So I think that they have this ability to be flexible, to maybe come up with new rules, but I think they don't have this strict framework for just being able to have strict relationships and not allow for any space for hallucinations or anything like that.
Mm-hmm.
Um, and it's probably easy to come up with architectures like this, but building them and showing that they actually scale up well is a different question.
Another very sort of interesting philosophical tangent, if say, or a clash between two particular trails that I found while I was learning about the entire diaspora of neurosymbolic systems was discrete logic versus the continuous representation, the tussle between them. Like I came across this Kurt Gödel's incompleteness, and it essentially provides a limit towards the knowledge system in terms formal system, right? And true things, there might maybe true things that cannot be proven, but in relation to then something like gradient descent, which is an optimization algorithm, but and has got things to do with the learning process of a system or a machine learning model or something. It somewhere in some way limits puts a limits on the computational computational solvability of sorts. And it's like if we have one particular facet of this entire thing that's putting a limit on the learning system, and another facet that is putting a limit on the knowledge base, how exactly are we expecting to expand this particular intelligent system into something that can maybe compete with human intelligence?
This is another one of these questions that I'll take apart because there is
Please,
multiple
please,
pieces here that I
please.
think are worth referring to. Uh, One of these is this discrete versus continuous nature of things for gradient descent, which is hugely important. And I actually have some collaborators who work on this space. Um, and then there's going to be the second part about Gödel's incompleteness. So I'll start with this one, and then I can move on to the more nebulous incompleteness questions. Um, I agree with you that technically things like logic or even text is difficult to do gradient descent over because it is discrete. Um, there are there are some really interesting papers in this space on approximating something like gradient descent on discrete spaces. Uh, Text grad is one of these approaches that I will highly recommend looking at. But the basic idea is, if you have a discrete space, um, sampling is probably the closest that you're going to ever want get to. And there is no reason to believe that that the human brain is running any gradient descent. Maybe running some kind of efficient approximation of it that makes sense on a neural network. But realistically speaking, it's probably doing some kind of sampling. And sampling is a process that you can do from a discrete space or from a continuous space, and it works pretty well. So, in fact, highly dimensional spaces. Before all of this, excitement about gradient descent and neural networks, if you look at how how computation in highly dimensional spaces was done, and say theoretical physics, as Monte Carlo sampling, you just like have these massively dimensional integrals, and you just sample them. And that used to be the way that we did this before everyone got really excited about gradient descent and everything has to be gradient descent. Uh, I think we might see more, algorithms that depend on some kind of sampling. Um, and I have a paper with my collaborators in which we try to look at how would you do optimization just in the space of prompts. If you try to do a chain of thought and you're like, oh, I have a chain of thought prompt and it kind of works well, but how do I find a better chain of thought prompt? That you need some kind of optimization on this space. Um, Obviously, you cannot run gradient descent on the prompt because there is no obvious way of doing this. But what you can do is, again, do a very particular type of sampling. In this case, we did Gibbs sampling, which effectively does some kind of evolution on prompts. So you can come up with algorithms that do some kind of efficient way of exploring the space, and then sometimes they turn out to have some kind of analogies to something you might see in nature. Um, in this case, if you do sampling in a very particular way and you do rejection sampling, in fact, this is closely related to what R1 actually does for reasoning as well. one of the main elements that they added to the whole pipeline was this sampling and a kind of RL framework. And that is something that moves you computationally into a slightly different space than just doing gradient descent. And potentially does something really interesting. Because then the way that you do sampling changes things a lot. And it explores a very different computational space. And since we're talking about computational spaces, this is naturally where you connect to, to things like Gödel's incompleteness and the questions of, what we can compute, what we cannot, or like, in computational space, this Turing incompleteness, Turing halting, and so on. It's unclear to me whether this is of practical or Turing halting is something that is of kind of practical relevance, but is also very theoretical. I don't know how much it's something that we should expect these models to really run into, to be honest. And the way I'll put it like this is these concepts, while they're highly inspirational for me, they say something about the foundations of math and being able to do math from this kind of first principles. But if we're not building a system just on like first order logic, there's a ton of AI research that I even partook in to some degree, that tries to create systems for first order logic, where you create an AI system that will be trying to prove theorems in logic or like very particular versions of logic. And there are these theorem provers, and trying to automate these theorem provers is one big field of research. I think Gödel's incompleteness very much clearly shows you that you will not go from that to AGI. Right? You're going to hit a barrier pretty quickly. But some kind of hybrid system that does kind of reasoning at different scales and understands that some, the rules of logic can be applied within this space, but that mathematics itself is just these islands that are kind of like not entirely connected. I think, in a way, language models or something like that is very well suited to that space. We have, through Gödel and others after him, we have very clear picture that mathematics is just this collection of ideas, and that there is no like single theory of mathematics or anything like that, and that it's impossible to actually have one. And and we seem to be okay with that. And maybe it's partially because we cannot there is not a single person who can comprehend all of math, and maybe they're not bothered by the fact that it's somehow inconsistent. This is kind of similar to the fact that the way that our brains work is we're capable of holding conflicting points of view in our heads at the same time. Cognitive dissonance is useful, and maybe it's fundamental in a way. By how it looks like with incompleteness theorems, like there is no way of having like one single uniform truth that everything else kind of follows from. But so for that reason, I think systems like language models at least are pretty good in this. They don't have to have somehow internal consistency. If you require a system to be, and I will get I might get some flack for this from some people who are really into systems that are provably secure and things like this. But if you want to have a system that you can prove everything about, I think it's very limited. There is a whole field of research that does try to write code that you have it's verifiably secure, and that's equivalent through like mathematical correspondences to showing that you can prove all of the theorems that this code implies. We will never, I don't believe that it's possible to verifiably show that an operating system could be secure. I think this is too complex of a system and I don't even know if it's consistent enough as a framework that you could do something like this. And that's just an operating system. If you look at the sum of what we do as a society with all the code and so on, it's very much verifiably not. Um, if you would compare that to proving theorems, a lot of those theorems are wrong that we're trying to operate everything on, and that's okay because they kind of work within some kind of limited applicability, and they're at least decent enough that you can scaffold things on top of. Uh, I don't this one slightly on a tangent maybe, but
What I mean, okay, then if we talk about something like intelligence, right? There has been a lot of debate and difference in terms of defining what it is, how it works. But in terms of when we talk about trying to build systems that are intelligent, does this intelligent entirely, and surely there might be degrees, it cannot be entirely this, entirely that, but to what degree is intelligence emergent from data and structure and pattern recognition, and to what degree is it informed through a model of physical reality? Is it significant to give sufficient amount of significance towards trying to train these models on data directly brought about from the physical reality, a model of the physical reality, structural reality, instead of just merely simulating stuff? Data that is entirely from simulation. Is there any sort of difference between the two approaches?
this is a question I've been thinking about a lot, and this one I don't know if I have a satisfying answer because it's going to be really painful in a way. I used to think that, or maybe I'll kind of this one we might spend some
Yeah,
time
yeah,
on,
yeah, please.
but I feel like um, we need to distinguish what we mean by definition of intelligence first of all, and then you might want to kind of go from there and what is like the functional difference. Um, and maybe creativity as well and things like this because we seem to care about not just if you're thinking of intelligence as just like information processing, this is a very
100,
weak definition.
100%, yes.
That is so these systems are intelligent. uh, a lot of things are intelligent by that, like a DVD player is intelligent by some kind of information processing definition. What kind of probably matters is that doing some kind of non-trivial operations on this, on this information that is given to you. We would probably say that most humans are intelligent, and some animals might be showing some intelligence. But the question is, I used to think that it requires some sort of reasoning, and it requires some sort of insight into your own internal states, and then doing some kind of operations on top of these internal states and so on. Uh, but it is not clear to me that you cannot get to it just from data. And by this I mean, if you have a large enough data set on the task in which you're going to be looking at intelligence, then if somehow the data set covers the whole space of what you would want to be testing this intelligence in, then you just you can train a language model on this. You could just train some kind of association on the training data itself. And if you're testing in the training data, then it doesn't matter. And we've known this, before LLMs became a big thing. Um, everyone was paying attention to just deep learning for things like, ImageNet and things like this. And all machine learning practitioners learned this lesson that you should not test on the training data. And we have kind of forgotten this lesson again. And this goes up and down. In the 90s, people also forgot about this, and then all kind of weird results came out in papers. But we now, then we finally felt like we understood that we cannot test on training data. But the problem here is that you cannot just not test on training data. The test data really has to be slightly out of distribution, a little bit at least, to test some kind of out of distribution, generalization. Uh, but if all you're testing on is kind of within the interpolation of the training data, then the system is intelligent just from the data itself. And that's where we're kind of sitting with language models. There are some very interesting examples of this where, if you look at the technical report for GPT-4, which was a while ago, um, it was doing really well on a ton of tasks. And it was even doing well on code forces challenges up to the cutoff date for the training data. And then it completely didn't do anything on the newer ones. So this is a clear case of you're just testing on training data, or like on the interpolation of the training data. Even if you didn't explicitly train on code forces, you did some kind of testing, and then you update the model a little bit, and you do graduate student descent or something like that, the equivalent of that. And you find hyperparameters that fit in. Overall, you interpolate nicely within this training data. And if that is all you really care about, if we somehow collected enough data from the internet, from the universe somehow, and built a really big language model, a really big neural network, it probably would be capable of reproducing all of human capabilities and all of our achievements and so on, because they would be sort of in the training set. Question is, do we do something more fancy than that as humans? I used to think that necessarily. I don't know if this is always the case. I think a lot of what we do is still kind of interpolating within the data that we have inside of ourselves. Maybe the trivial thing that we do is that we're very multimodal systems, and we're really big networks. So maybe we do something that is really fancy, that we're like interpolating between modalities. I suspect that a big part of our reasoning capabilities, and that seems to be the case if you look at like fMRI studies, is the kind of activity throughout the brain, throughout different brain regions. Some of them responsible for language, but some of them are responsible for things like visual imagination and and a ton of other, and going to just emotional responses and things like this. If you put mathematicians in an MRI machine and you look at how their brain activates, it's pretty broadly activated. So this tells you that we're doing some kind of reasoning. We're activating not just the network responsible for what you would think is clearly necessary for the task. We're doing some kind of multimodal processing, and maybe there's some kind of interpolation between all of these, where the interpolation itself doesn't really lie in the space of any of these single modalities. So you can imagine that thinking happens sort of in the space that is not really language based. It's not really language, based on any single thing that we have a modality for. And yes, if we're getting here kind of philosophical and so on, Wittgenstein was this philosopher in the 20th century, and he famously wrote this Tractatus Logico-Philosophicus or something like this, where he tried to formalize thinking, and he ends it with whatever is something. It goes along the lines of the only things that are worth that have any value are the things that we can't really talk about. And I'm completely butchering all of philosophy here by saying, I'm co-opting this and saying, maybe the things that are really interesting are somehow lying in this space of interpolation that our brains do, that is not just in language, but it is doing something across all these modalities. And if you want to be like slightly, insane, then you can connect this to our experience of conscious things like qualia and so on. It is sort of lying in this space of interpolation between different modalities, different senses, and so on. So things like the standard, what is your concept of red? It connects to a lot of memories. It connects to different sensory inputs and things like that. So that concept itself lies not exactly in a language space. So I suspect a lot of our computations happen in that way. Uh, but if you build build a neural network that is multimodal in this sense, it will also do computations in that kind of uh, you tokenize everything in the same way. This is just a trivial way of doing it. You tokenize images, text, speech, maybe sensory input from some kind of robotic arms and things like this. Uh, it might be capable of doing the same kind of computations that we do. Uh, Maybe if you train it on enough data, it's going to be equivalent to a human. So that is one way of looking at it. But I think that there is something to be said about efficiency, and we're slightly more efficient, I think, arguably, than language models are these days. And that's mostly the data efficiency. You don't need to feed so much data for new tasks. And this is where we get into the definition of intelligence. So one definition of intelligence is being really good at one particular task, and that is a very restricted definition of intelligence. The original definition of Turing's was kind of really broad. Like you talk to something and you figure out is a human or is another machine, or it's a machine. Arguably, we're past that point. We can't really always distinguish whether we're talking to a human being or not anymore. But there is a really interesting different definition of intelligence that came out in maybe 7 years ago or something like that, maybe 6 years ago, by Francois Chollet. He's the guy who created Keras. He wrote this paper on the measure of intelligence, and I highly recommend it to every person I meet. Probably my favorite paper in the field of AI. It's a tour de force in which the paper is split into three ways. The first one is basically criticisms of definitions of intelligence that exist. Second one is proposing a new measure of intelligence, and the third one is actually creating a data set for measuring it.
What is the name of the
And the
paper
data set
again?
you may be familiar with, it is the abstraction reasoning corpus AGI
What is the
challenge
paper again?
on the measure of
Okay, 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 okay,
intelligence
okay.
by Francois Chollet. And in it, I love the paper because partially, the first third, he's just dunking on Turing a lot, and for a good reason. Like that was foundations of the field, and it has moved on quite a bit. But here's a take on this. That is the main one that he gets to. We should distinguish being really skilled at something and being able to acquire new skills efficiently. And he posits that intelligence is really the ability to uh, learn new skills fast. And if you're skilled at something, but just this one thing, that is not really intelligence. That is just ability to excel at the one task. So by this definition, systems like AlphaGo and so on are not really intelligent. Really good at playing Go, but that's about it. Language models maybe show a little bit of intelligence, and they're starting to show some kind of intelligence. But it is the fact that I show you one or two examples of a new task, and you can kind of pick it up as a human, and it is really challenging for AI systems to do so. So this is, he formalizes this in some kind of information theoretic ways, and he actually proposes what these measures of intelligence are. But suffice to say, they're about sort of a very efficient way of acquiring skill in a new task. This assumes that you have some kind of knowledge base that you can acquire new task, like that these tasks are at least in principle doable by the system that is attempting to do this. So he proposes like what is like the minimal number of a minimal knowledge base that you would probably need to even start thinking about this problem. And the specific data set he proposed, the benchmark he proposed for measuring intelligence, is still something that is a challenge for a lot of vision language models. Uh, that is the ARC AGI challenge currently. Um, Granted, the newest reasoning models are starting to, show promise at it, and they're solving it in high enough rates that they're, I will say for the first time we're seeing significant improvements. Um, but these are very simple tasks. They're difficult enough that a single person probably is not going to get 100% on this test. But if someone gets, the levels of scores that O3 or R1 get at it, you'd be, you know, you would feel pretty silly about yourself because you would see everyone else excelling. I when this data set first came out, I wrote a few papers on it, and I had a whole group of undergrads at MIT trying to solve these problems. And I realized that a group of three undergrads together from MIT can solve this challenge. But there are some problems that one of them makes a mistake on. So you need a panel of humans to get like 100% accuracy on this test. And it is a data set in which each task is given two or three examples. And then you're needing for each new task, you need to come up with what the rules are on these examples that were given to you in the training set. So this is very data sparse, and you just need to be able to come up with new rules. And this is where neuro-symbolic systems, I think, really will need to come in to fully solve this.
That was a good way to tie it back to our original discussion. But okay, I'll take a segue. You were talking about earlier a little bit about this, and it just clicked into my mind. But how much of what you do, the work that you do, how much of it is just fancying these different possibilities or things that can be? You know, trying to figure out different variants of how to do a particular thing, how to solve a particular problem. Just thinking about it, not trying to do anything, not trying in the implementation or execution aspect of it. Just sitting with yourself and thinking.
I do an inordinate amount of thinking about things like this. I do a lot less of trying to implement it. Um, Partially, my background is as a theoretical physicist. So a big part of my PhD was just laying on a sofa and thinking about very complicated problems. So that still is very much a mode of way that I like to do my research, at least at the thinking stages. Um, the other pain point is that like to actually do this kind of architectural thing, this is where I said like scaling matters. We have entered this weird stage of doing research in which I could come up with a tiny little prototype, but then very quickly, if I come up with an idea for doing something like this, I I get into the point of if I want to test this in a scale that has any relevance for what's currently happening in the research field, I need to train a billion parameter model. And I'm at Microsoft, I have access to resources like this. There is a finite, even for me, there is a finite amount of just doing this kind of random explorations. Uh, if I'm okay with training a tiny model that I can run on a local GPU, that's unlimited. But like once you start wanting to look at how things scale and whether you can do these kind of things, that you have to start prioritizing your ideas. In fact, yes, a lot of this is me just ideating about things and then maybe throwing some ideas to an intern or a student of some sort
I think
who might want to go with this and
I
experiment with
think
it.
that is the privilege that you invariably get once you are deep enough and thorough enough with your particular subject matter. Because if you've just picked something up, you can think about it, but regardless of how hard you try, you may not be able to go as in depth with it as you want. But when you get a little bit thorough with the basics of that particular domain, it rather actually helps you out counterintuitively maybe, to spend more time thinking and brainstorming about these different ideas and possibilities that may be beneficial in some sense or the other. Would you agree with that?
This this is a good question, kind of just about general like research styles. I think I agree with you. You do need to somehow dive deep into a field a little bit, at least, to be able to do this kind of ask relevant questions. Maybe let's put it like this. It's really easy for you to just read a paper and look at it and think, okay, this is something that inspires me to do something else. Uh, Unobvious whether this is something that people have tried before and it has failed in some kind of particular ways. Likely, a lot of things that I have come up with, people have tried before and they just didn't write a paper about it, or they wrote a paper about it and I didn't find it. Which, to be honest, the discovery has become impossible, especially in this field of AI. The amount of papers that are written daily and put online is daunting to the level that I used to try reading papers daily. This has become impossible to keep up. Um, so in a way, my answer to you is going to be maybe you need some kind of foundations and think a little bit about the foundations of what the fundamental issues are, and then you can think about that kind of broadly. You don't need to really stay abreast of all the recent developments, especially like the very technical small things. Those are details that don't seem to really matter as much. And in fact, we were proving this time and time again that like you come up with some kind of architectural improvements and things like this, they don't really matter. Scale matters. Some kind of fundamental things matter. There's high level principles matter. The technical details, you can change them up a little bit, and you're going to maybe get a percentage of two more on some kind of benchmark or something like this. Um, so what really seems to matter is maybe thinking deeper rather than trying to have a stack of papers that you kind of go through. Uh, I don't know how you attain this without talking to the right people. So I think talking to the right people is for me the first step when I enter a new field. And I had to go through this when I switched from doing quantum gravity research to machine learning and neuroscience. Um, and I was just strategic enough that I talked to the right people and they kind of like pointed me in the right directions. Uh, So I think asking people for, what's some of the big open questions in the field? Those open questions are going to be open questions for a long time. And you can at least start kind of building from there to see like what is the things that are like truly fundamentally difficult. I mean, you can start chipping away at those things in some kind of consistent way.
Is that the same sort of template that you would advise undergrads to take? Because again, when you're an undergrad, maybe your first year, second year, you're just starting out with the rigor of that particular subject matter, and at that time you cannot really figure out, as you said, the right questions to ask. And when you talk to these people, how then do you make sure that even though you are not that efficient or prolific with the magnitude of value that you can maybe take out of the knowledge of this particular subject matter expert that you are talking to, but still to some degree you are able to take something of value that might propel you maybe a little bit forward in terms of your understanding and perception of whatever the topic that we are talking about.
This is a great question. So, uh, to be honest, I suspect that undergrads are getting more and more insanely good as the time goes by. I don't fully understand how this is, but I remember when I was an undergrad, my expectations of myself were nowhere near as high as I see expectations of undergrads these days having of themselves. Uh, and nonetheless, I will say uh, there is a very different it's very unlikely that you will be a second year undergrad and know what are the relevant questions in research. Uh, it has happened on occasion that I have met someone who was absolutely brilliant, and they did. Uh, I don't know how they got to that. That often is because they started doing research somehow in high school. Um, and I've actually been there myself. I've advised a high school student who got a NeurOps paper with me. It's not impossible, but it rarely happens, and these kind of things are far and few between. Realistically speaking, what you probably should be doing as an undergrad is try to join, a lab over the summer. You have a choice as a maybe throughout the year. You have a choice as a computer scientist. You can get an internship with a company or try to do research over the summer. And that is a really difficult one. If you want to be a researcher, then I think doing some research over the summers is really useful, and not do like every single internship at the company that you can. Um, but doing research throughout the year is the thing that really, I think, changes things for you. Even if it's like really part time, just a little bit here and there. Um, it takes a while to, and when I say do research, you try to join some kind of lab that wants, needs assistance, and hopefully you join a lab that is actually going to be interested in your growth as a researcher and not just use you as a resource. And that is a whole different talk about how to like choose advisors and things like this. Um, but I've worked with a ton of undergrad students when I was still in academia, and I don't know. Not, I think within my 4 years at MIT, I advised over 25 undergrads. I don't know exactly how many, um, and uh, consistently, I found that the ones who actually did stay for like a longer term and actually uh, worked on and had the interest in working on actual more slightly more fundamental questions, they eventually were the ones who uh, would attain some kind of slightly deeper understanding of the field. I think that helped them long term. It doesn't always help you long term in the sense that like if you dive into too difficult of a topic initially, the one issue you might have is that you will have less papers than some of your peers who are just like spitting out, uh, pieces of code that are useful. So I think there's some kind of balance there that you want to strike. Um, Ideally, you're working on some kind of challenging thing that still gives you research, papers out of it, because then you're competing against people who are just these machines that somehow have multiple papers at the end of their undergrad. I don't know how that happens. Um, and But I think where you really attain the ability to get good at research questions is doing a PhD. That is in big part, I think, suffering through I think PhDs unfortunately are dependent on some level of suffering in which you uh, kind of learn that some of your ideas are terrible and some of your ideas kind of work out. Most of your ideas are terrible. And there is something to be said. I talked about the rejection sampling earlier. Like you really have to learn how to reject
Yes,
ideas,
yes. Hmm.
uh, because occasionally, and this you see this a lot with some people. The first idea that they have is the one they go with. It sometimes works out, but most of the time it doesn't. And this is not just in research. This is just generally in life. Um, you have to kind of iterate on some ideas occasionally, um, and not necessarily that you have to be critical of every single like idea that you have. Sometimes you have to, give it time and develop it and nurture it. Uh, but I think this maybe connects to, again, reasoning models in a weird way. Um, for us to be able to be good researchers, and the then question is, how do AI systems become good researchers? You need to be able to build intuition, and intuition comes from experience. You have the ability, and this is intuition at different levels. You have intuition, you know, maybe just at the level of, I kind of have a feeling how to do this proof in a, in a mathematical setting. Or I have an intuition for, like, this is a research question that is going to lead to something really interesting, or this is something that will, whether I find an answer to it or not, probably doesn't matter as much. Will have less impact or more impact. Um, but you eventually build up an intuition for, this is going to be a problem that will be really difficult. And that is an important intuition to build, because sometimes, realistically speaking, you're going to come up with a problem that sounds easy, and then you're stuck on it for 2 years, and you realize that things are miserable. And sometimes, so failure, learning to fail multiple times is really useful, because that really gives you this ability to intuit what the correct path through reasoning in the spaces. And this is, um, in a way, intuition is something that, that language models do have, as this, just experience based things. But we can take intuition and we stitch these pieces of intuition together to really, like, create this chain that gets us to, like, I have a feeling that this is true, and then that might be the case. And you kind of, like, once you have the ability to stitch these pieces of intuition together into a longer term path, and you kind of look at a problem and you feel like, I think this is where it's going to lead, and you have a path in your head. um, that's when you're kind of maybe starting to become, a researcher who can look at the field and make some kind of guesses as to whether this idea will make sense or not. um, at least that's what I'm telling myself now. I don't entirely know if this is all there is to it.
I mean, okay, I think that was sufficing, but again, taking back a domain specific detour, or coming back rather to the domain specific questions, I was thinking about the absolute Turing test, instead of just judging a system's intelligence based off of conversational or interactional data points. When you talk about the entire three-dimensional perception, in terms of physical reality, that is incredibly difficult for n number of reasons. But when you talk about VR technologies, where it enables you to sort of facilitate a human interlocutor of sorts, that can, because I assume that it is, again, from a technical perspective as well, relatively far more easier to try to mitigate absolute Turing test in a virtual reality than the physical one. What I want to ask you is the mechanics of it.
Yeah. uh, Great. Yeah, great segue into some of my other work. um, uh, I agree with you. Robots are super popular these days. They're finally making some progress, but the progress is still slower than most people think. It is very much uh, driven by the need to get to, like, impressive results, but most of robotic work doesn't generalize yet. It really is. It works in this one specific setting. And while I was impressed by this kickboxing match the other day that they had in China between the two robots. It's still very much not something that is, uh, you look at it and even if they were wearing human suits, like you would know, and they're very far from it. Uh, so yes, VR or some kind of like virtual like settings are obviously like the right place to um, not just test intelligence but let it grow. You need some kind of environment that is general enough in which you can teach actual like multimodal concepts to these systems where they can learn by experience. So that's kind of where my work has been heading in the last few years. It's there's a few things that these systems don't currently have, and they don't even have access to it. Um, I'll give it this. I'll give this to you, for example. It's very clear that in the way that we acquire intelligence and acquire skills and things like this is heavily dependent on us perceiving things continuously. You need some kind of continuous sensors and some kind of, our brains have very particular type of biases that allow us to learn things. We don't start with a completely blank, a randomly initialized neural network. We have some kind of algorithms that are kind of in there to like help us do things. One of those seems to be just tracking objects in the visual field, like changes in visual field and continuity of time. That seems to matter a ton. If you would just be, if you take language and you take images and things like this and you just flash them randomly sampled uh, at a neural network like a baby, growing up, I think it would be pretty terrible, and it probably would not learn anything useful. Uh, and it might take about the same amount of data that it takes to train GPT models to train a baby to actually do anything useful. Uh, but if you have a setting in which it can, a system like this that is learning can have continuous inputs into itself, it will be actually learning from it, which they currently don't do. But if you had like a continual learning system that had these continual inputs and ability to act in this setting, then I feel like that is clearly something that they could learn. They could use some kind of biases and the training algorithm to speed things up and to get better at it. So uh, honestly, I think the only setting in which, outside of actually building physical robots, you could try to explore this kind of multimodal, information integration about conceptual things. Because I mean, maybe two modalities are enough. Maybe you don't need this, but I feel like the ability to interact with something and having control over the environment and the way that you interact with it is pretty critical to at least some understanding. Um, Another aspect of this is, so because of this, I've been working in this VR space and creating, using generative AI to create environments so that you can actually have environments to like train these systems on, in principle. There's another aspect which is I'm lacking, but a lot of people have, which is visual imagination. I suffer from aphantasia and I cannot imagine anything in my head. But a ton of people I hear are capable of closing their eyes and seeing things. Um, and I think it's pretty critical as a capability for a lot of people. I have my versions of this that are very mathematical and I think in more graph based ways. Uh, but it probably will be useful for a model like this to have a capability to simulate something in its head and then take actions based on these simulated things. So you want to give simulators that are general purpose enough to an eventual intelligent system like this. And we have some kind of simulators in our heads for physics. If you can predict the trajectory of something, so you have some kind of simulations. Like if I pick something up and I throw it, I kind of know where it's going to go. And some of it is visual, some of it is just some kind of simulations that happen in some kind of circuits in your brain. And we have ability to propose a simulation and come up with like a possible version of where this is going to go. And we have a ton of intuitive physics like this. But a lot of people also have the ability to simulate in their head the conversation between two people and how it might go, or what will happen if a particular situation happens when I'm driving a car. Ability to come up with hypotheticals and then test them. That would be highly useful for a system that is trying to improve. Um, the applications to self-driving are pretty obvious, but the applications to a ton of things in AI will be pretty obvious. Hence, I've been kind of working on a system that uh, allows prompting into virtual environments.
Is there any sort of study in regard to what are or what apparently will be the consequences of humans living in these programmable realities? Like, would there be a factor of if you, for a prolonged period of time, are living your normal existence as you do in these virtual environments, somewhere to some degree, your efficacy at interacting with the real world in the real world diminishes? Is that a factor that is being studied?
Now that I know that it has been studied, but this is a pretty important plot point in a sci-fi novel by Charles Strauss, Accelerando, uh, in which I will agree with you. If you had a virtual environment that you were kind of like living inside of the simulation of, and you had some sort of root access to changing this reality in some way, and the ability to spin off sub simulations inside of this big simulation and things like this. That is in a hypothetical scenario in which this is, the simulation is pretty good. It would be better than, you would have a lot more control than in the physical reality. Um, so in a way, uh, the root version of reality would be kind of boring
Boring and
by comparison.
boring, and even to some degree, I mean, the thing with, okay, something like crypto
Limiting.
limiting certainly, but maybe take an example of something like cryptography. The thing with
Mhm.
cryptographical systems is that they aren't truly cryptographic. Why? Because they aren't truly random number generation, right?
Yeah.
And that is the sort of difference between reality in terms of how we perceive it, our experiences. It's to a large degree uncertain in terms of the sort of physical sensational experiences that you have with the world, which, in order to, if you want to, if you're looking forward to simulating that in a virtual environment, it would require, I assume, some quantum level random generation of all these different uncertainties, these markers and headers of uncertainties, which might be extremely tough to pull off, I assume, with our current technology.
I would think that was the case, but then the other day I saw someone create a random dice generator using particle decay.
Okay.
So it's just a tiny little project by an enthusiast on the
Uh-huh.
internet. But I don't see a reason why you couldn't have like just embedded a tiny little chip in a computer that is just looking at particle decay, and that gives you a random number generation that is truly random. That is relatively easy to
What's it?
do.
Okay. Maybe dive into this particular notion a little bit more. How does this creation of this virtual environment, or environments rather, work in tandem, or maybe adaptation to human emotions, intent, and cognition in real time through this sort of approach that we have started discussing right now?
Mhm. Uh, Great question. One, this is very hypothetical because I'll give you the version of it that exists currently and the
Hmm,
hypothetical
hmm,
that
hmm, hmm.
that would be cooler. Um, right now, when we try to do this kind of, I co-lead this effort we call speaking the world into existence. And the idea there is that we apply all of these generative systems to be able to go from an idea to a simulated reality, a simulated virtual reality. And uh, realistically speaking, given the current latencies and existing language models and other AI systems and so on, when you go from this prompt to somewhat playable version of this, a very simple version of like this kind of virtual reality, nowhere near visually realistic anything like this, but it might have some kind of dynamics and might explore some kind of concept. That that takes a half a minute currently. Uh, Sometimes more, sometimes less, depending on how the amount of things that you want to put into this simulated reality, how complex you want it to be, which specific language models you're using to run some of the code generation and things like this. Um, does the system do self feedback? All of these questions kind of like, realistically, we build this with multi agent systems that are kind of like asynchronous and they feed things to each other and so on. Uh, but uh, it takes time for now. If you could imagine somehow, first of all, making this thing more robust and actually would be creating consistent simulations all the time that were really great, and then you could speed it up. And let's say that you could speed it up so that it is running faster than real clocks. Like, could I generate a simulation within, a few milliseconds and then run it at a faster clock than the real clock that we have in the universe? Then you start opening up yourself up to possibilities of simulating some kind of thing really quickly as the reality is like presented to you. Like you're entering a room and looking at a situation and trying to, you know, the very simplest, you're playing pool, or you're playing some kind of games of chance or something like this, or you're playing some kind of like sport like thing. You could simulate a lot of these behaviors, maybe multiple times. And this will not be, for a specific setting. This will be you're creating a simulation for that concrete situation that you're in, and you can go through multiple training scenarios. And if you can do this fast enough, and the AI system is in this situation, this is a thing that can spin up the simulations, experience them, learn from them, and then integrate them. And if it could do this in a matter of a few seconds, then it has somehow like entered the situation and then has gone through multiple training scenarios in a few seconds, uh, and be ready to at least respond to it with some experience in a completely novel situation that it has not experienced before. That you know once we make jump to that, and I suspect that is going to be some number of years before we have systems that run this fast. um, but this is not far off science fiction. Like if you look at the speed at which the latency hasn't really improved that much, but we have reduced the cost for all of these models. They run more efficiently. They do run faster over time. Um, you can imagine that you could try to do something like this faster and faster.
So essentially,
So you open yourself up to the possibility of actually having being able to simulate a social interaction, and maybe multiple versions of the social interaction before you actually at the beginning of having this interaction, or as you're having this interaction.
so it is latency.
Right now, I was talking about physical
Hmm.
simulations, but this could be simulated the other agents and how they might respond and things like that.
So currently, it's like latency is the primary issue with trying to maybe. to some degree or the other achieve.
and quality of answers. Like these
Okay.
models are still not
Hmm,
that great.
hmm, hmm.
Like it's a different thing if you are trying to do just latency on potential conversation, the paths that this conversation might take. I think that you could potentially simulate pretty well these days, pretty fast. If you're trying to simulate an actual version of of reality, in which visuals matter, physics matter, and things like this, that requires you writing code to implement all of these things, verify that this code actually is compilable, compile it in real time, interact with the system, things like that. So there's a ton of latency there right now.
Okay, a completely hypothetical thought trail, but you just mentioned it, so I just want to explore it. But what if we change the sort of physics of this virtual environment? Like, you can fly. Are there any repercussions to that in terms of, well, the dissonance that it will create from your existence in a virtual space and real space, which I think there would be something. And secondly, the computational aspect of it. How much I think it would be extremely tedious to basically you'll be creating the laws of physics from scratch and trying to make it all work in tandem. It's bound
Hmm.
to be tedious. Do you see it working in some way or the other?
Uh, great question. The first one, I have no idea. To be honest, uh, what impact this would have on you, just like perceiving reality and experiencing with it, it probably would be pretty bad for an AI system, uh, because it will have expectations from this like simulated realities that it could not implement here. If, on the other hand, it was kind of exposed to the ability that uh, the modes of locomotion, the degrees of freedom that are available to it are variable and change simulation to simulation, and it can design what these things are, then you have at least a system that is flexible and learns to adapt to different settings. So that is the kind of thing that you would want to have, that you would then embed into a modular platform. A system that might have a robotic arm, or maybe not. Maybe it has just like some sensors for looking at things, or maybe it has like wheels, or it suddenly has legs, or things like this. If for a single model to be capable like across these different degrees of freedom and input and output modalities, uh, then yeah, that might be helpful. But I agree that there is a there is a very high risk that it would learn something that is completely useless to it in a given setting and the real world. So that is a big concern, and honestly, that is one big issue that has existed in robotics, which is the simulated environments don't really transfer to the real world exactly, and they don't transfer exactly enough that like it is a big issue. Even if you have a really good simulation of the real world, it pales in comparison to all of the small things that happen in the real world, where the motors on the robotic arm don't exactly work like the simulated ones and things like this. So there's small disagreements, and then the whole thing falls apart. That has always been the case in the field. Like it's getting better, uh, but maybe simulating a system and giving it the flexibility and all of these parameters changing, that is enough to at least train our system so that it's capable of doing this, and within some kind of flexibility. So maybe not giving it the ability to fly if it doesn't have jet engines or something like this. Uh, but so that is the answer to the first bit. Uh, the second bit, yes, it can be tedious to generate fresh worlds from scratch all the time. Um, Having a learnable repository of things that you have built before to reuse and recombine, that's kind of useful. It's kind of like in Minecraft. You could start from digging everything from scratch, or you can craft materials and then craft more materials with those and so on. So like you can be modular in a way, and reuse some bits that you've learned before. And it's the same with scales that we have. Like, you might try to uh, learn, you know, it helps that a ton of things that we have to do are compositional in nature. It's you know things like writing. In this case, building the whole simulation of the world. There's elements to it that you could reuse, or you could reuse and then modify rather than just have to create from scratch. So things like needing to write the whole like physics simulation of something. How many times do you need to do this? Like maybe for each situation you're going, it would be a really weird world in which you would have to redo all of the things from scratch all the time. Um, we could not operate in a situation like this if you are constantly thrown into an environment where everything has changed. Uh, so if you can reuse some elements and then you're building these simulations, but every single time you're building it, it becomes easier because you can reload just most of it and just change a little bit. That simplifies things a lot. So you want to have some kind of growing library of things that you can efficient, and then the question becomes how if it grows too big, you need to be able to somehow efficiently search through this library, maybe synthesize useful things. That's where dreaming comes in for us. Like we learn things and then we kind of like simplify things for ourselves, and we actually integrate this information. So you'll want some kind of dreaming stage to this, like learning what's the useful bits that you're using.
How about the aspect of, okay, maybe shed some clarity upon this. Is the ability to perform self feedback for a model something that can be equated in some loose form towards self reflection, self introspection, or retrospection that we humans understand? Or is there more to it in terms of a world where reasoning machines that can form hypotheses, self correct, and influence their decision based upon the learnings that they gather? Is there something more in terms of that would be needed to enable them to form philosophical discussions, build or imbibe or evolve a value system, things of that sort? Or is that something that we have to actively put some effort into developing? Or is it something that you see as a natural progression of how this entire domain is evolving?
um,
Because okay, can
Here
I chime
is
in? Like, I'll
no,
tell you the motive behind this
yes.
question. Uh, it's coming from a place of maybe trying to better understand the coexistence between intelligent systems, machines, robots, etc., and humans. Like, uh, I was reading about this particular happening that you might be aware of, where Claude AI, quote unquote, blackmail their developers of some sorts, and it just sent me
Hmm.
into a thought trail where I was thinking about the entire approach that we as researchers or developers of these sort of new forms of intelligence and beings of sorts eventually take to maybe just better the process in terms of how these machines think. Like, is there some way that maybe instead of approaching it from a perspective of developing them, a researcher that takes the approach of raising an intelligent system or model might be more beneficial in terms of how we humans approach building that system? Because Sure, the discussion that machines aren't emotional, it's a lot of mathematical formulations going on in the back end, that is justified. But humans, researchers, most of them, they, in some way or form, their approach might differentiate in terms of from what mental framework or point of reference they are coming from. Because once when you think about, okay, I'm developing a model, you do not really inherently pay much attention to all these different factors that I just asked you about. Value systems, maybe
Mhm.
philosophical abstractions, discussions, talks about ethics and morality. Can an AI hold a conversation about that with a human being? How about we think about that? And that is the sort of motivation or place where I'm coming from while asking you this question.
Okay, let me try to answer this. I, I like this angle on the introspection for this. Um, and this is, I'll say, I think so. To answer this question, the answer is pretty yes. But that was a long question, and I'll try to break up why I'm saying yes. Uh, it is clear to me, and I think to a lot of people, that we need some kind of introspections, or you might want to call it some kind of recursion or something, where the model is looking at what it's thinking and then thinking about what it's thinking, and that is pretty crucial for a lot of tasks where the first initial thought might not be the right one. Um, and this is such a complex question. I'm sorry. This is going to be a little bit broad of an answer as well. Um, I'm of the belief that any system that will be eventually deployed, while it might be down the line something that becomes a single model, the best models for like this kind of complex behaviors that they're expecting out of this are going to be multi-agent systems where there's like multiple, and those are easier to think of. You have modular. You have modular systems in which there's each module responsible for a different thing, and there are a useful setting in which there is only one agent that outputs something or like speaks, and then there is some kind of thinking that happens behind the scenes. And you can imagine taking all of this multi-agent kind of like complicated. There's multiple agents, and somehow putting a black box over it and calling this a single model. And effectively, that is what is going to be the case. That's how our brains kind of seem to work. But behind the scenes, there is some sort of multiple information streams that come out, and then they get somehow integrated. Then the system kind of looks at it and tries to do some kind of introspection, maybe integrating all of these things, satisfying some kind of constraints that it might have. Um, and that's kind of where maybe this question of values is interesting. Um, right now, language models don't really have a place for values. The only place that they have in values is in the training data. The training data most definitely has had AI that is malicious. And in fact, while it had training data on like the Asimov's laws of robotics, no one really believes in those in most fiction and in most documents that these things are trained on. So the fact that, I don't want to call the cloud model just a stochastic parrot. They're more than stochastic parrots. But in this case, the fact that it, tried to blackmail an engineer, a hypothetical engineer who like might be turning it off, you know, that's exactly what you expect from the training data. Like, what else did you expect? Like, you run this kind of experiment, and you're running it with the assumption that the obvious thing that it has to do is blackmail someone. uh, because there is no clear values that have been embedded into it outside of maybe guardrails that we put on top of it where it cannot talk about a topic. But the reasoning inside that it might first, before it hits those guardrails, the reasoning is going to be based on the data that it has. And the data is obviously you're going to blackmail someone rather than allow yourself to be killed or allow an AI system, a rogue AI system. There's many arguments from storytelling that just make sense. So in that sense, I don't know if this particular example of Claude, doing something like this, is more than just repeating what you would expect from the training data in a novel way. I'm not claiming that there is this particular passage in some kind of novel or anything like this. So it is doing something slightly better than just repeating verbatim, but it is nonetheless. I would be surprised if it decided based on, without RLHF, in which you're trying to put guardrails on it, that it should not do this because it's immoral. I would have been honestly more surprised if it could explain that morality. And the reason is it's not clear that these language models are necessarily developing as complex, subnetworks as we have in our brains. And they are getting more complex over time. The work from Anthropic on the biology of LLMs is really interesting. It's very illuminating. There are sub parts of these big systems that have learned specific things, and in this case, I still don't think that it has a value network inside of it. And I don't entirely know what that is even for humans. Like, we have values that we kind of learn, but they're flexible over time. They change. We learn them somehow. There's some work that we know from neuroscience on how exactly they function, but we don't fully know it. And I think it would be very illuminating to try to build a system that has some kind of values, because those then would be really useful not just for the kind of societal thing, but it would also be the thing that would be useful for steering its behavior and for giving it curiosity about doing things and allow it to be somewhat more not just reactive to prompts, but actually driving, have a self drive. And I think that is something that I would be surprised that there's not a ton of people already working on. Maybe not in the next iterations of Claude or anything like this, but this is the kind of research that I would highly, if you're wanting to get into something, this is the thing to get into. Like, find what would be the equivalent of a system having self motivation, and that self motivation has to come from some kind of value system. And maybe it's a value system that it can update, ideally. But if that value system would be explicit, then that at least could be like one place where we might have any hope of controlling them, whether you want to control an AI system or not. That's a different conversation on where you stand on this. I think these things are tools; they're not personhoods yet. Uh, it becomes a little bit complex if we do assign them some kind of agency and personality and so on. Right now, they're just tools, and if we treat them as tools, we really should figure out how to make them controllable, and being able to somehow use a value network that we could influence somehow, or have at least insight as to like what are the kind of like core values that this thing holds, and hope that it's not lying to you, and like we be able to look at the fact that it's not right now they're not lying yet to us as far as we know, but there is nothing stopping a complex network like this in principle from developing internal goals and obfuscation and some kind of like if it learns that someone can look at these values and then learns how to obfuscate them, that I think would be showing that it actually has values, that it has learned to have a self-drive for preservation, things like that. Right now I don't think any of these systems are actually doing any of this, and they're just, again, Their self-preservation doesn't go beyond just this kind of text completions.
One of the perspectives that I saw this from, and obviously I do not know what the nitty gritty is going on in the back end, but uh, the thing about tools is that a drill machine of sorts. You plug it in, you turn it on, it'll keep on, you know, drilling until you plug it out from the main unit. But if you try to put your hand over it to stop it, it isn't going to stop because that isn't its purpose. The purpose that you've defined it when you turned it on is to keep moving, keep on drilling. And it was a very
Mhm.
interesting analogy that I correlated it with is maybe to some degree the value system, quote unquote, that currently is defined for all these AI systems is to achieve a particular goal while doing a particular task.
Mhm.
And the thing with Claude's, if I'm not wrong, was that it was performing some mathematical computation, and the developer was sort of shutting it down or stopping it from performing it while it was doing it. It was midway through that entire process. And it was then when it sort of
Mhm.
rebooted or did something. Again, things are not entirely sure, the nuances of the matter. But as you said, it is part of that aspect that maybe it is not as nuanced as that these things have already developed the value systems or the morality to lie to us or hide stuff or maybe do things in a greater order of magnitude in terms of all these things.
Yeah, the thing that they're lacking though is this introspection and respecting this internal value system.
Yes.
We seem to not we sometimes break our values, but then we get some kind of internal turmoil and we get upset about the fact that we did something that didn't satisfy these values. Right now, language models don't have that. There is not enough recurrence inside.
Yes.
And there would have to be some kind of sub recurrence, not just recurrence on the whole network level. Um, Once we figure that out, and the ability for the model to update its own weights based, or like some part of the weights based on what it's done, then I would truly like. Then we could talk about this kind of questions. But right now they're static. LLM as it's deployed, it's just a static thing. There are some big recurrent networks that people are exploring. They're still not continually learning ones. So, we have to really make the jump from these static systems to systems that learn over time. And that is a big fundamental issue that we have. We don't entirely know how to do these things. You could do some kind of LoRa fine tunes as you go on. You could build a system like this, but that is building like an architecture on top of just if you give a language model a tool to change its own weights, that would be very slow, but maybe you could start exploring this kind of like a system that updates its own values.
Yeah.
And then maybe you could talk about this kind of. I feel like then, because once if values are static and they're not influencing anything, then, uh, they, or at least not in a consistent way. You need some kind of feedback, and this feedback needs to imply something for the model long term.
It is again. I do not know how much it connects back to that, but how you initially talked about uh, symbolic reasoning serving as a scaffolding during the training period. You know, where
Mhm.
maybe loosely putting it, serving as a curriculum of sorts that is later phased out once the patterns are encoded, and it keeps on updating the neural weights by itself. Something of that nature.
Yes, I think this test time scaling will have to somehow at least change aspects of like some small part. Like maybe not the whole model has to be rewritten, but you could imagine some kind of low rank like updates like LoRa kind of things in a small part of the network or like small aspects of the network. so that you don't update your brain the whole time as you're doing everything. I don't think our our visual cortex gets like fundamentally rewritten all the time that we see something, uh, and things like that. So I think there's like aspects of our brain that are
True,
mostly
true.
frozen. Some things that maybe update a little bit. We would. I think that our value network is not, it does not update fast, but it does. It has the ability to update. Similar, and I think big parts of our brains are capable of updating, but I think the updates are pretty slow. Maybe they happen during dreaming only. I don't know. I have no idea entirely for this.
Yeah, even with neuroplasticity, how neuroplasticity works. When you're learning something new, it's not that immediately you are ingrained with the skill set or the cognitive ability to do a particular thing. It's the gradual changes in your neural wiring that eventually enables you to make that shift.
Yeah, so I think that this shows that at least, but we don't even have that for language
Yes,
models
yes,
right
yes.
now. All we're doing is we're collecting more data from the users to interacting with it, and then we retrain, we fine tune it, or we retrain it, or something like this. But that's very different than I go to sleep and I wake up and I can learn to juggle in a pretty short period of time. At least three balls, four balls is difficult. Like uh, that's a skill that you can learn, and well, it's a manual skill. But the equivalent of that, you can learn new skills in a short period of time. But you will not master them or anything like this. Um, and sleep seems to be pretty important. I think the sleeping phase and awake phase are something that is probably going to become more, explored in language and AI models in general. There have been some like sleep awake explorations, um, but I guarantee that we'll see more of that.
Dr. Andy, my final question to you for this particular conversation that we had is, what would be your word to humanity at large?
Uh, you've put me on the spot here. Um, since this is a conversation about AI, uh, and this is maybe not to humanity at large, but it is to the people who are actually working on these systems. And they will probably not listen to this because they will not care. But I think that we owe it to the to humanity to be a little bit more intentional in how we think that these things that we're building are going to influence everything. Right now, it's I have a lot of most of my friends are not actually in the tech industry, and I see a divide that is happening between people who work on AI systems or who are super excited about them, and then people who really are afraid or just hate it. Um, and it is for a good reason because we're actually at, at best we're just adding something that is really annoying, in our products that like you have to interact with. At worst, it is displacing, slowly displacing all of the creative tasks that we might want to do. I don't see a reason that language models like these will not get good enough that it will not replace me. Uh, we should figure out, a version of future that we can be excited about, that we will build towards that, and that still has us like, not just doing menial tasks. Um, so the call maybe here is people in this field are heavily inspired by fiction. We need better fictional description, depictions of what a positive version of future kind of looks like. And I love dystopian fiction, absolutely, but it cannot be the motivating force for building these things. It cannot be that cyberpunk is your favorite genre and you're going to be building towards this terrible future. We need something that is motivating. You can see that the movie Hair has been heavily motivating for all of these chatbots. Uh, we need something that is motivating equally and like pushes us in the right direction.
Cheers to that. Dr. Andy, thank you so very much. I really appreciate it, even though I think
Thank you so much.
I took a lot more of the time than I promised you I would take. So thank you for bearing with that. Thank you for bearing with all the different thought rails, messed up questions, all the different messy, tedious stuff that I ventured
Mhm.
you into. But thank you so very much for this entire conversation.
Thank you so much.
And
Well,